Welcome to lecture 1 in aldehydes and ketones. So, in this lecture, we'll discuss the introduction part of alkanes and cycloaldehydes and ketones, the nomenclature, how to prepare aldehydes and ketones. These are reactions that we have seen already, but we'll see them again as a review. And introduction to a specific type of addition called nucleophilic addition reactions. Next, oxygen nucleophiles and nitrogen nucleophiles. So these are the types of nucleophiles that you're going to see in aldehydes and ketones. So with that, let's start introduction. So what is the difference between aldehydes and ketones? The only difference is that the only thing that is common in both of them is that they have what we call a carbonyl group. A carbonyl group is a carbon that is double bonded to an oxygen, and on each side they have a specific functional group. So this is the idea behind. This is the idea behind a ketone. So this is a ketone. An aldehyde has one side chain and CHO group. So if you have CHO, then we call it an aldehyde. If you have a COOR, then we call it a ketone. So these are very important compounds in both biology and industry. For example, simplest aldehyde is used as a preservative. For example, formaldehyde is used to store human remains. It can also be used to store, it generally is used in labs, in anatomy labs to store, uh, human remains where if you wanted to, you know, have dissections. So this is the liquid they store in. The second one is acetone. Acetone is the common one that you use to remove nail polish. So it's a commonly used solvent, specifically a organic solvent. Next. Other compounds that involve aldehydes and ketones is vanilla. Vanilla flavor comes from a compound called vanillin. So these are artificial flavors that you can replicate. Cinnamon flavor can be can be taken out by cinnamaldehyde. And R-carbone is the spearmint flavor. Benzaldehyde gives you the almond flavor. And most other compounds such as progesterone, which is one of your hormones, has a ketone group on it. And the testosterone generally also has a ketone group on it. So these are compounds that generally have uh, ketones and aldehydes embedded in the structure. So there are four. So let's discuss the nomenclature. How do you name these compounds? So there are four discrete steps to name an aldehyde or ketone. So it's similar to the procedure that we used with alkanes and alcohols. So the first step is to identify and name the parent chain. The second step is to identify and the name of the substituents that are attached to the main group and assign a locant to each substituent and assemble the name alphabetically. Remember that the difference here is that we do not consider this C double bond O as a substituent, we consider it as the parent chain. So for aldehydes, what we do here is we replace the dash E of any alkane with dash AL, butanal. Remember that AL represents aldehyde, OL represents alcohol. This is a commonly misused difference that you might find confusing. So, and the second rule is that parent chain must also always include the carbonyl cation. So, the cation that you are using must always be included in the parent chain. So, if you have a parent chain, for example, this is an octane, but if the same compound has a CHO group, then we include that as the parent chain. So, whichever is the parent chain, that should be the one that has the carbonyl carbon. The second, the aldehydic carbon is always assigned the number one. So even before double bonds, even before the priority for any substituents, we always give priority to the C double bond structure. So always give the number one carbon assignment for the aldehydic carbon. Next, for ketones, replace the E with one. So what we do here is, for example, if it's butane, and if one of the carbons has a double bond, we replace it as butanone. So one is for ketones, Al is for aldehydes, Ol is for alcohols. And the parent chain must include the C double bond O group. For example, if this is the structure, then we also always write the number, the smallest number for the carbonyl structure. So it should have the lowest number possible. And you can express the number before the parent chain or before the suffix. So you can write it as 3-heptanone or heptane 3-one. So whichever one is okay for that. Next, the configuration of the chiral center is indicated at the beginning of the name. So when we write the configuration, we always write it at the start. So if it's R here, we write it R at the start. So when you have an aldehyde next to a ring that is named as carbaldehyde, so any aldehyde that's named after the the ring is always called as carbaldehyde. For example, if this double bond O was inside the ring, we would have written it as a ketone. But if it's outside the ring, so notice that this is cyclohexane and it has a CHO group on it. So we write it as cyclohexane carbaldehyde. So this is how we write the nomenclature for this compound. So all the IUPAC names also are recognized as common parent names. For example, formaldehyde is a common compound, that a common name used as a IUPAC name. Acetaldehyde, which contains an acetane group, is also considered the IUPAC name. Benzaldehyde is also recognized as an IUPAC name, even though it's a common name. Now, let's try some problems. So let's try and name these structures. So the first things first, always remember the one that contains the carbonyl group always has to get the lowest number possible. So which means that this contains number 1 here, 2, 3, and notice that in this side we have a double bond, so we'll have to go this side. So 4, 5, 6, 7. So there are 7 carbons in total, and on the fourth carbon there is a double bond. So notice that because of the double bond, it can be having a two-sided structure, which means we can name it as an E or Z structure. Notice that because of the double bond present in the middle of the compound, we can name it as an E or Z structure. So let's try and name it as per the structure. So first things first, write down the parent chain. The parent chain is heptane, but it has a double bond at the start, so it is heptanal on the first carbon. So we can write heptanal directly. So, or we can write the number heptane 1L, and in front of it, the first thing we want to make sure is there is a ketone, there is an ene group at fourth point. So always write heptane 4-ene 5Al. Right, so heptane 4-ene 5Al, sorry, heptane 4-ene 1Al. So that's the part. So which parts are done? So we have named the double bond structure, we have given the aldehyde name, and the next one is a hydroxyl group on the 7th carbon. So we can write it as dash 7 pole. Right, so or we can write it as hydroxy, but I wouldn't recommend writing it as hydroxy every single time. So try to name it accordingly. So how would you name this structure? Here is based on the idea of alphabetical order. So the first one that gets the alphabetical order is Al. So we are going to write alphabetically all the substituents. So 1Al, 4-ene, 5-ol, and then we can write the naming here is based on the structure that we have here. So here, if you split it like this, notice that on the double bond structure, this is one side on the bottom, this side is on the top. So which means it's E. So we can write that this is E structure, right? So or the other name would be, we can write it as E 7-hydroxy hept 5-ene 1Al. So this is the name that you would have written, the other name for this structure. Let's try the other structure. Here also notice that there is a double bond. So there are two double bond O groups. So we have to name it according to which one gets the lowest number. So when you name it here from here, you get a 2 here, but when you name it from here, you get 3. So we are going to name it in this direction. So 1, 2, 3, 4, 5, 6, 7, 8. So this is the name here. So based on this name, what can we write for the compound structure. Now, I think we missed something here. So there is a propyl group here. So E3 propyl. I'm sorry for that. So in the second structure, we also have an E structure. So we have an E structure. And on the first carbon, there is hydroxy. So one hydroxy. On the fifth carbon, there is a propyl group. So 5 propyl. Next, you have on the third carbon, there is ene. And in total, you have 8 carbons. So you can write it as oct. So 5 propyl oct. So it's on the third carbon. So 3 ene, right? So you have one, so which is the double bond O, and 2 comma 6. So 2 comma 6 in dione. So this is what you could write it as the naming of this compound. So let me give you another one so that you can try this on your own. Right, so this is the structure. So pause the video right here and try to name the structure. Notice that there is a chiral carbon. This is a chiral carbon. So try to write it either it's R or S at this carbon. So don't forget about that part. So let me give some more problems for practice. So pause the video right here and try to solve these problems. So let's continue on to the next topic. So the next topic, let's talk about preparing aldehydes and ketones, and we'll try to review these reactions. The first among them is the oxidation of primary alcohol. So when you oxidize the alcohols, you end up getting an aldehyde group. So which under further oxidation will lead you to a carboxylic acid. So when treated with a strong oxidizing agent, primary alcohols are oxidized to carboxylic acids. But if you don't want that to occur, you use to create aldehyde, we use a mild oxidizing agent. So remember that when you use a strong oxidizing agent, then you get acids, so carboxylic acids. But if you use a mild oxidizing agent, you end up getting aldehydes because the mild oxidizing agent does not have the enough capacity to further oxidize to result in carboxylic acid. The second one is ozonolysis of alkene. So when you use an alkene and you do ozonolysis on it, it splits the double bond into two parts and attaches oxygens on each of them, resulting in the formation of aldehyde. So ozonolysis will cleave the double bond that you have there, and if either carbon atom bears a hydrogen atom, so the aldehyde will form. If there is no hydrogen, then it ends up forming a ketone. So that's the idea behind aldehyde preparation when you have an aldehyde. Next one is hydroboration and oxidation of terminal alkynes. So when you use hydroboration of terminal alkynes, that results in an aldehyde formation always. So when you use an internal alkyne, it forms ketones, and when you use terminal alkynes, you get uh, aldehydes. So hydroboration oxidation here is an anti-Markovnikov addition reaction of water, meaning that it adds oxygen and water, but then following by tautomerization and resulting enol, it forms an aldehyde. And the next one is ketone preparation. So the first one, when you have oxidation of secondary alcohols, that results in ketone formation. So a variety of strong or mild reagents can be used to oxidize secondary alcohols. So the resulting ketone will not undergo further oxidation. Remember that aldehydes do undergo further oxidation, but ketones do not undergo any further oxidation. So next one is ozonolysis of alkenes. When you have alkenes that have multiple side chain groups on them, under ozonolysis they create ketone structures. So they cleave the double bond and create ketone structures. Again, when you have terminal alkynes and acid catalyzed hydrolysis, that creates the formation of Markovnikov addition of water. So remember that anti-Markovnikov addition results in the formation of aldehyde. Markovnikov addition results in the formation of ketone. The last one is Friedel-Crafts acylation, which we discussed in the topic on aromatic compounds. So where you use an acyl group that results in the formation of uh, acyl ketones. So the aromatic rings that are not too strongly deactivated will react with an acyl halide in presence of a Lewis acid to produce an aryl ketone. So this is the reaction here. Now let's talk about nucleophilic addition reactions. So the carbonyl carbon here is an electrophilic carbon. So because this is derived from resonance and inductive effects. So the carbonyl carbon here has oxygen on it and a carbon on it. So because oxygen has a higher electronegativity, it can end up creating a resonance structure where the negative charge can jump to the oxygen, leaving the carbon as a carbocation. And in terms of the inductive effect, because oxygen has a lot more electrons than carbon, it results in more the electron distribution directed towards oxygen. So because it has both effects, the problem here is that it can cause both these problems. Because of both effects, the carbonyl carbon can be attacked by nucleophiles, forming a new sigma bond in exchange for the C double bond O. So what happens now whenever a nucleophile attacks the carbocation, the electrons on the carbocation will go on to oxygen, resulting in a negative charge on the oxygen and nucleophile bonding to the double P carbon. So where it changes from an sp2 hybridized structure to an sp3 hybridized structure. So aldehydes in general are more reactive towards nucleophiles than ketones. The main reason is because of steric effects, meaning that aldehydes here are generally less sterically hindered because they have only one hydrogen on one side, but a ketone has two side chains on each side. So because it's harder to have this effect. The same thing with next electronic effects. So aldehydes generally have a large del plus on the carbonyl carbon because there is not much structure around it that can distribute the positive charge. But here there is much more less positive charge here, and there is more positive charge on the aldehydic carbon. Next, some nucleophiles generally require acidic conditions and some require basic conditions. For example, Grignard reaction requires basic conditions for it to undergo nucleophilic addition. So a strong nucleophile means that the reaction is under basic conditions. So Grignards, halides, hydrides, all of these are strong nucleophiles. So if you have a strong nucleophile, the reaction generally occurs under basic conditions. So under basic conditions, all nucleophiles react with carbonyls by the same reaction mechanism. So how is the reaction mechanism work? So the first thing is the nucleophile attacks the carbonyl carbon, and once it touches the carbonyl carbon, it attaches itself to that carbon, and then the oxygen gains the negative charge on it. The oxygen then attacks the proton on water, resulting in the formation of an alcohol group on it. So the nucleophile attacks, forming a negatively charged intermediate, which is then protonated upon acidic workup. So this is the idea behind how a nucleophilic addition reaction generally works. So let's start with acidic. So aldehydes and ketones react with variety of weaker nucleophiles as well under acidic conditions. Remember that stronger nucleophiles need basic conditions. Weaker nucleophiles need acidic conditions. So what's the difference between basic conditions and acidic conditions is the process in which, or the order in which, the reactions occur. In basic conditions, it's first nucleophilic attack and then proton transfer. But in weak nucleophiles under acidic conditions, first is the proton attack and second is the nucleophilic addition. So the first thing that happens is that the carbonyl group gets attacked by the acid, resulting in the formation of that OH with a positively charged oxygen. Then it creates an electrophilic oxygen. So what happens now is that the nucleophile attacks the carbon, and once it attacks the carbon, the electrons go back to the oxygen, making it neutral back again. So that's the difference here. Notice that in under basic conditions, first you will have nucleophilic attack, second is proton transfer. In acidic conditions, first there is proton transfer and second there is nucleophilic attack. So the carbonyl is protonated to form a positively charged intermediate which cannot be attacked by a weak nucleophile. So that's the difference here. Here you will get a strong nucleophile and here you have a weak nucleophile. Now, the acidic conditions are required in order for a weak nucleophile to attack the carbonyl carbon. The main reason is because it has to have a powerful electrophile. So once you create a powerful electrophile, only then is it possible for the reaction for the weak nucleophile to attack the positive charge. So protonation of the carbonyl makes it a better electrophile. That is the reason why we end up doing the reaction in acidic conditions for weak nucleophiles. Now, so when a nucleophile attacks on a carbonyl group, so the equilibrium depends on the ability of the nucleophile to function as a leaving group. So remember that again, it has to be a good leaving group. So when will the reaction be favored is when the nucleophile is a good leaving group. So only then, if it's a really good leaving group, the equilibrium will favor the starting ketone. So this will be favored. So depending on the ability of the nucleophile to function as a leaving group, you can decide the equilibrium that you have. So in this lecture, we will try to cover the following nucleophiles and their reactions with ketones and aldehydes. So first one are oxygen nucleophiles, which is water, alcohols and diols. Sulfur nucleophiles, which is sulfide and sulfonates, sulfoxide, sulfonates. Sorry. Next one is nitrogen nucleophiles, where you have amines, so primary amines and secondary amines. Hydrogen nucleophiles, which are ALH4 and BH4 minus, and carbon nucleophiles, which are Grignard reagents, cyano group, and a little larger phosphocyano group. These are phosphocarbons. Sorry, these are called phosphines. I forgot. So these are called phosphines. So let's start with oxygen nucleophiles. So in the presence of water, a ketone and an aldehyde is in equilibrium with its hydrate. So generally, the ketone and aldehyde always combines with water to form diols. The equilibrium generally does not favor the formation of the hydrate only when it is except for very simple aldehydes. So the rate of reaction is generally slow unless acidic or basic conditions are used. So only when you have acidic or basic conditions are used, the reaction rate is generally slow. You want to enhance it, we use acidic or basic conditions. So under basic conditions, OH minus is a nucleophile. So OH minus acts as a nucleophile, attacks the carbon, attaches to form the OH group, and finally undergoes proton transfer and creates the two OH groups that you have. So which means remember that this is a base catalyzed reaction. So why is it base catalyzed? Because there is first nucleophilic attack and then there is proton transfer. That's the reason why it's a the base catalyzed hydration. Under acidic conditions, what will happen with water is that the carbonyl generally is protonated. So, and H2O is the nucleophile. So what happens first? The oxygen attacks the proton, causing it to form a positively OH group. And once the water as a nucleophile attacks the carbon, the electrons are given back to the oxygen, resulting in extra notation where there is an entire water molecule that gets attached. Because of that, one of the water molecules attacks the uh, proton and leaves the electrons back to the oxygen, causing it to form OH groups. This is acidic conditions because first there is proton transfer and then there is nucleophilic attack. So remember the difference here. If it is first nucleophilic attack and then proton transfer, that is base catalyzed reaction. In an acid catalyzed reaction, we get first proton transfer and second we get nucleophilic attack. Next, what are the things that you have to keep in mind when drawing the mechanism? So under acidic conditions, a mechanism will only be reasonable if it avoids the use or formation of strong bases. So only when you have a strong base cannot exist in an acidic environment, only then under acidic conditions a mechanism will be reasonable. When you have a basic condition, a mechanism will be only reasonable if it avoids the use of formation of strong acid. So a strong acid cannot exist in a basic environment. So this is the difference between the two nucleophiles. Next, alcohols can attack ketones or aldehydes. So when you have an alcohol that attacks, it creates alkoxide ions, which is OR minus. So the OR minus gets attacked and creates acetal. So this is an example of a compound where it forms from acetone. So we call it acetal. Under acidic conditions, there is only one ketone or aldehyde that reacts with two alcohols to form acetals. One of them is p-toluene sulfonic acid and sulfuric acid. So these are the only two acid conditions where given ketone and aldehyde will react with two alcohols to form an acetal. So what happens in this reaction here? Again, notice that this is an acidic condition, which means that first there is proton transfer, the ketone gets attacked by water, creates an OH group, and then undergoes nucleophilic attack by the alcohol, resulting in the entire carbon attached to that, and then the acid, the negatively charged atom will attack the oxygen and remove the proton, resulting in the formation of again. So first thing happens is that OR group is taken out. Next, another acidic group. So the OH group will attack another acid and then again create two hydrogens. So the two hydrogens will leave, the entire molecule will leave and create a double bond OR and finally gets attacked again to form a double OR group, an acetal group. You don't need to remember the exact mechanism, just know that this is the reaction in which the reaction occurs. So the acetal formation is an equilibrating process, which means that for simple aldehydes, the acetal is favored at equilibrium. But for most alkenes, the acetal is not favored. The reason mainly is because it is too complex of a structure to be stable. So that's the reason why it's not favored. When you have simple aldehydes, it's much more favored. For ketones, it's not favored. Next, if a diol is used, then both equivalents of the alcohol come from the same compound and a cyclic acetal is formed. So when you have the combination of diol and ketone, that creates what we call hemiacetal first and then finally creates a cyclic acetal. So cyclic acetal is when you have two oxygens that are bonded to a single carbon where the original ketone group was. So where the original ketone group was, you get a cyclic carbon structure. Now, acetal formation is generally reversible and can be controlled by adding or removing water. So, if you want to favor acetal formation, we remove the water. If you want to convert an acetal back into ketone, water is added. So, remember the difference here. So, when you have the only thing that changes is the removal of water and the addition of water. So, this is how we can maintain the structure. Now, let's try and understand how this mechanism works. So, how the following synthesis can be established. So the first thing we are noticing is that we are converting an ester into a primary alcohol. So which means that we are removing oxygen. If you are removing oxygen, it basically means that we are trying to use reduction. So reduction meaning that we are going to use lithium aluminum hydride, which will leave the ketone unchanged because ketones do not react with LAH. And here the problem is using LAH would reduce the ketone as well. So you cannot use LAH. Solution is to use a protecting group for the ketone. So what we can do is we can use a protecting group for the ketone to shield it from the effects of lithium aluminum hydride and let the ones that are not protected, the ones that end up causing the problem. So how do you protect it? So the most common protection is to create a cyclic acetal. So we add water to the original compound. We remove the water from the original compound, creating a cyclic acetal, and then the cyclic acetal is then reacted with LiAlH4 to create the final alcoholic structure. Notice that acetals are a way of protecting the ketone group because they can be easily reversible. So next one is a hemiacetal. Hemiacetal is an intermediate that is formed in the conversion of ketone or an aldehyde to an acetal. A hemiacetal is where you have an alkoxide and an alcohol group on the same carbon that's attached. So we call that a hemiacetal. Hemiacetals are really unstable. That's the reason why they are generally really difficult to isolate because there's the equilibrium either favors the aldehyde or the acetal based on the conditions that we are using. So it either forwards in this direction or in this direction. That's why we can specifically remove them. But we can remove cyclic hemiacetals. So we can remove it as cyclic hemiacetal. So when you have a cyclic hemiacetal is generally possible when you have a compound that contains both carbonyl group and a hydroxy group. For example, let's say if I have a structure that has a carbonyl group and a hydroxy group, we can create a cyclic hemiacetal, creating the reaction when you're in acidic medium. So the same thing, the original common example of a hemiacetal is actually uh, glucose. A good example of a cyclic hemiacetal is glucose because these are important in carbohydrate chemistry for them to function as a general structure. So we'll discuss this much more about the glucose structure in carbohydrates. So for now, just remember that glucose in its cyclic form is also a cyclic hemiacetal. Why is it a cyclic hemiacetal? Because it's a double bond, it's an oxygen group and an OH group adjacent to each other. So that's why it's a cyclic hemiacetal. So when you have an acidic conditions, as aldehyde can also react with primary amines to form what we call an imine. An imine is a double bonded nitrogen with a side chain. So when you have a double bonded nitrogen with carbon, we call that an imine. Amine, when you have a nitrogen that's bonded to hydrogens, single bonded ones are called amines, double bonded ones are called imines. So the reaction requires acidic conditions to work. So that's the reason why it requires an acidic condition. So the first thing that should happen is, again, because it's an acidic conditions, so it undergoes the nucleophilic attack and then it undergoes proton transfer. So and it undergoes removal of the proton on it, and finally it creates the double bonded NR structure. So it generally is the imine formation. So this is what, when you have a nitrogen nucleophile, what happens in the reactions. So you don't need to remember the exact reaction, just remember what the nitrogen nucleophile can do. So the nitrogen nucleophiles are amines and generally bases, and they generally consume the hydrogen catalyst. So the ammonium ion is the acid catalyst for the reaction. So the ammonium is RNH3 plus. So the ammonium ion here is not acidic enough to protonate an aldehyde or ketone, but it is acidic enough to transfer a proton to a negatively charged oxygen in the second step. So this is the common way in which we see nitrogen nucleophiles. The other one is an enamine. An enamine is when an aldehyde or a ketone interacts with a secondary amine. A secondary amine is where the carbon creates where you have the double bonded carbon attached to a nitrogen. We call this an enamine. So remember, the name itself says enamine. So that's how you can remember it. So it's a double bonded carbon that's attached to a nitrogen group. So that's why the name enamine. So again, the reaction also requires acidic workup. So when you take a ketone, it ends up creating an imine under primary amines. When you use a secondary amine, it creates enamines. So remember, primary amine creates imine and secondary amine creates enamine. So this is the main basis of your reaction, so that you have to remember. Now, one of the common reactions that we use that we can reduce the structure back to its alkene is what we call the Wolff-Kishner reduction. It's a two-step synthesis converting. We are trying to convert a ketone into an alkene. So first thing that we do here is we take an ammonium ion and create an imine, and the imine, under further reduction in the presence of potassium hydroxide, creates the alkane. So the first step is the imine formation between the ketone and hydrazine, which is the primary amine, and the secondary reaction is the elimination of that entire group, resulting in the formation of amine. So the removal results in nitrogen formation, nitrogen removal, whereas the hydrogen goes back and forms bonds with the carbons that was originally bonded to the nitrogen. So note the many similarities between acid catalyzed mechanisms that we have discussed here. So one thing, remember to always note that when under acidic reactions, the reaction species should either be neutral or have a formal plus charge. If you have a negative charge, it's not going to be an acidic reaction. If it's a positive charge, only then it's an acidic reaction. So with that, we end lecture 1.